our objectives for this lesson are to identify when a chemical reaction has taken place, to write a balanced chemical equation, and to use that chemical equation to do quantitative analysis. Quantitative, remember, meaning numerical. So we are going to be able to use these chemical equations to do math. Okay? We're not going to get through all of this today because this is a very long lesson of notes, and then there's a bunch of practice that I want to do with you. But we're going to get started. Okay? Recall that a chemical reaction is the process by which one or more substances are changed into one or more different substances. So when we have a chemical reaction happening, we start with certain things and end with at least one new thing. Often more than one. In a chemical reaction, we call the original substances reactants. The new substances we call products. And the total mass of the reactants must equal the total mass of the products. This is because of the law of conservation of mass. So, throughout today, you're going to hear me talk about reactants and products. Those are new words that we have to become familiar with. So, if you are looking at the chemical equation written, your reactants are always going to be written on the left side, and your products are always going to be written on the right side of the arrow that's in the center. And however many atoms of one substance you have on the reactant side, you must have an equivalent number on the product side. Doesn't mean it has to be in the same arrangement, but the number of atoms cannot be different because of the law of conservation of mass. During a chemical reaction, no mass is created or destroyed. It's only rearranged. A chemical equation can be written to describe a chemical reaction. Our definition, therefore, for chemical equation is something that represents, with symbols and formulas, the identities and the relative molecular or molar amounts of the reactants and products in a chemical reaction. So to summarize that in a little bit less wordy fashion, a chemical equation is something we use. It uses symbols and formulas to show us what atoms are in a chemical reaction and their relative amounts. It won't tell you exact amounts, it'll tell you relative amounts. So it's like a formula unit, where it doesn't tell you exact amounts, but it will tell you the smallest whole number ratio required to satisfy it. Okay, so now that we know what a chemical equation is, let's talk about some times when we're going to use one. In order to know for certain that a chemical reaction has taken place, we have to gather evidence that there is a new substance that has been formed. So before we ever write a chemical equation, there has to be a reaction. If there's no chemical reaction, there's no need for an equation because no chemical change has happened. So what evidence can we find that supports the idea that a new substance has been formed? Well, we did a lab where you saw some evidences, and here we're going to list those. Okay? The signs that indicate a reaction has most likely taken place include the evolution of energy as heat and light. This just means that when there is a change in matter that produces both heat and light at the same time, it's highly likely that a chemical reaction has taken place. If you have just light being produced or just heat being produced, this may not indicate a chemical reaction, but when they are together, there's a strong case for a chemical reaction having taken place. So, which reaction produced heat and light? The gummy bear sacrifice, right? When we dropped the gummy bear into molten potassium chlorate, it produced a bright purple flame, some sound, and if you had been touching the container, a lot of heat. It's very exothermic, okay? A color change is another indication that a chemical reaction may have taken place, okay? Often an indication of chemical reaction, but not always. If the only thing you saw happen was a change in color, you need to do some more digging before you just slap a label on it and say it was a chemical reaction, because some changes in color can be physical, right? For example, if I melt or if I freeze water into an ice cube, no chemical reaction has taken place there, but the ice cube is oftentimes white in color, whereas water is clear, right? And that has to do with the fact that gas bubbles were trapped in the ice when it froze, but that's not a chemical reaction. It's just a physical change, okay? So if color is the only indication, look deeper. But if there are other things that are happening along with a change in color, it's a pretty good indicator. So which reaction did we have a change in color?
The one we dropped it changed to like a gelatin.
There was a color change in two of them, right? So when we dropped the cobalt chloride into the lime water, it went from a white color and a pink liquid to a like blue solid. And then we also had a change in color when we added the phenolphthalein solution to the base, right? It turned a bright fluorescent pink. Okay, and those are both indications that a change has happened. The next one is production of a gas, okay? The presence of bubbles in a mixture can indicate that the production of a gas, which is good evidence that a chemical reaction has taken place. Okay? You do have to be wary, though, okay, that the gas wasn't already dissolved and just released. So if I handed you a bottle of Coke and you opened the cap, it would fizz, correct? But there's no chemical reaction taking place there. It's just gas that was dissolved in the liquid becoming undissolved and coming out of the liquid. No chemical reaction. The gas was already there. We just couldn't see it while it was sealed because it was still dissolved. So you do have to be wary, because not every time that there's bubbles does that indicate that a chemical reaction has happened. But if there were no bubbles in either liquid and you poured one into the other and all of a sudden it's bubbling, that's a pretty good indication that a gas was produced. Okay? And production of a gas, since the gas wasn't there to begin with, would mean a chemical reaction would have to have taken place. And the last one, which chemical reaction produced a gas? Baking soda and vinegar. Good. And the last one would be formation of a precipitate. Okay? When a reaction takes place where two chemicals are dissolved in liquids, and then you mix those two liquids and the resulting product is a solid, then a chemical reaction has likely taken place. Okay? And we call that solid that's produced during that reaction a precipitate. So when you dropped the drops of cobalt chloride into the lime water, a blue solid formed. You could tell that it was a solid because it stayed clumped together. It didn't dissolve into the liquid, right? They stayed into little clumpy bits. It didn't turn the whole lime water solution blue. It produced clumps of blue, which is an indication that it produced a new solid that didn't dissolve in either of the liquids that were in there. So that is a precipitate, and that's a new product. Indication of a chemical reaction. Questions about how to tell when a chemical reaction has taken place. Okay. It's good to note that sometimes chemical reactions take place without visual confirmation, and so you can only figure out that they've taken place by a chemical analysis, by taking the products and running chemical tests on them to discover if they are new substances. So not all chemical reactions can be spotted visually, but lots of them can. A properly written chemical equation can summarize any chemical reaction. These are the requirements that you must meet in order for your chemical equation to be considered correct. Okay? And I'm just going to go ahead of you here and say, writing a correct chemical equation is a skill that takes time to master. So if you cannot do this right away, please don't give up on me. We are going to get you there. Okay? It's just a skill that requires lots of practice because there's lots of moving pieces. Okay? First, the equation must represent known facts. So that means you need to represent in your equation all of the reactants and all of the products. Okay? You can list these based on an experiment. That's how most chemical reactions start. Somebody does an experiment and tests and discovers all of the products. Or if you are like us here in class, you will get them mostly from reliable sources. Okay, so either I will tell you which reactants and which products you are going to have, or you will need to look them up. Okay? But all of them must be present. Your chemical equation cannot be correct if you don't have all of the products listed or all of the reactants listed. Your equation must contain the correct formulas for the reactants and the products. Okay, so remember all of those skills that we just practiced for writing formulas for molecular and ionic compounds? They're going to come into play here, because a lot of times you're going to be given a sentence that tells you what things were reacted, and you're going to need to take those words and change them into formulas. So remember your rules for writing formulas. And then elements that are not in compounds are written as their chemical symbol. Okay, so if I reacted something and one of the resulting products was just sodium, then I would write Na. I would use its chemical symbol. There are a couple of exceptions to this rule. Sulfur doesn't tend to just exist as a single sulfur atom. It usually exists in a little molecule where 8 sulfur atoms have bonded together. So if you are producing sulfur, or if you are reacting sulfur with something, you're going to write it as S8. The same thing is true for phosphorus, which tends to be in groups of 4 phosphorus atoms. And then the last exception would be any diatomic molecule. So you'll remember we've talked about some diatomic molecules such as oxygen gas, where oxygen tends to exist as 2 oxygen atoms bonded together and not just one solitary oxygen atom floating around. So we would write it as O2 instead of just O by itself. There is a list on page 255 of your textbook that will give you the common diatomic molecules. Okay, and I will read a couple of them off for you, but this list is available on page 255. So some common ones would be hydrogen, nitrogen, oxygen, and fluorine and chlorine. Those guys all tend to exist as gases and they're diatomic. And then bromine is a liquid, it's usually diatomic, and iodine is a solid, and it's usually diatomic as well. So meaning for all of those, you would write their chemical symbol with the subscript 2 to indicate that there's 2 atoms bonded to each other. So if somebody told you they were going to react chlorine gas with sodium to make salt, okay, you wouldn't just write Cl plus Na. You would need to write Cl2 because it's diatomic. This matters later on. The law of conservation of mass must be satisfied. This is the last and one might say most important thing required in order for your equation to be considered correct, is your equation has to obey the law of conservation of mass. Which means we can't create or destroy atoms, so there must be the exact same number of each atom on both the reactant and product side of the equation. Coefficients, which are small whole number multipliers, can be put in front of formulas and change the relative number of atoms without changing the chemical formulas. So let's say, for example, that I'm reacting hydrogen gas, which we just learned is diatomic, so it would be H2, with oxygen gas, O2, to yield water. Currently, this is not correct, right? because I have more oxygen on one side of the equation than I do on the other. But I can't change the subscripts. Okay? It would be really easy to balance this equation by simply putting a little 2 here, right? Now we have the same number of oxygen on both sides. But there's a problem with this. H2O is water. H2O2 is dihydrogen dioxide, and it's poisonous and toxic to drink. It's not the same thing. So I can't just write that little subscript in there. So instead, I'm going to use coefficients to balance this. So instead, I'm going to come over here and I'm going to put a 2 in front of this. Okay? So that changes this, and instead of saying it's just one atom of water, one molecule of water, or 1 mole of water molecules, now I'm saying I have 2. So really, on this side of the equation, now I have 4 hydrogens and 2 oxygens. But that's still not balanced, is it? Because how many do I have on the other side? 2 hydrogens and 2 oxygens. Is there a coefficient I could add to the other side to balance this? Yes, I could put a 2 in front of the hydrogen, and that would yield a total of 4 hydrogens and 2 oxygens on both sides of the equation. Okay, so this is just a short little taste into balancing an equation. But you see how I can use the coefficient to change the relative number of atoms without having to change the chemical formulas, therefore leaving the factualness or the accuracy of my formulas intact. Steps for writing balanced equations. Okay, here we go. Into the chaos. It's really not chaotic, but it feels like a lot when you first see it. Step 1, identify the names of the reactants and the products and write yourself a word equation. A word equation is an equation in which the reactants and the products in a chemical reaction are represented by words. So if we were writing the same equation that I just did, we would just say hydrogen plus oxygen yields water. And I ran myself out of room here, but water would be on this side. Okay. Some kind of word equation. Bear in mind that a word equation is only descriptive. It's what we call qualitative, meaning there's no numerical data given to you. From a word equation, you cannot tell how many of each atom is present. Okay? Because you are a good chemist and your brain is already translating the word equation, you can, but if you were just looking at a word equation for chemicals you were unfamiliar with, you would not be able to identify number. Step 2, write yourself a formula equation by substituting in the correct formulas for the names of the reactants and products. A formula equation represents the reactants and products of a chemical reaction by their symbols or formulas, but it is still only descriptive because there will at this point be no numbers, just subscripts. But they often include more information than a word equation might. For example, formula equations often include a parentheses with a description of which state of matter the substance is in. We go back to the example that I've been using. The formula equation would be the first equation that I wrote for you, where we wrote H2 plus O2 yields H2O. Okay. But we would probably include information such as this is a gas, and this we would put L for liquid. Okay? Unless, of course, the reaction produced water in a gaseous state, in which case we would write gas. Okay? So, little more information. We know what state they're in, and as Autumn pointed out, we do have some numbers, we do have subscripts, so we know the number of atoms in each molecule, But because we don't have any coefficients yet, this isn't balanced, we don't have any kind of ratio. We don't know what it looks like in comparison when it's truly balanced, because at this point, this equation is not balanced. Next step is to balance the formula equation according to the law of conservation of mass. This step is done through trial and error by changing coefficients on both sides of the equation. So remember how I said this is a skill that you have to practice? Because it's trial and error, you just have to work through it and try it and add coefficients and count up how many are on each side and see if you are correct yet. Because changing something on one side of the equation often changes more than one atom, like with water, we changed the number of oxygens, but we also changed the number of hydrogens while we were at it. There are some guidelines you can follow to help you simplify the process of adding coefficients. Okay? Step 1, balance the different types of atoms one at a time. So try to get one atom balanced before you move on to a new atom. Okay, we worked to get the oxygen balanced, and then we worked on the hydrogen. Start by balancing elements that are combined with other elements, but that only appear once on each side of the equation. So sometimes you will have elements that are in multiple reactants or multiple products, and if you try to start with one of those, you'll drive yourself a little bit crazy. So start with one that only appears once on each side of the reaction, but that is connected to another atom. Then, if you have a polyatomic ion, remember polyatomic ions are combinations of atoms. When you're balancing the polyatomic ion, don't balance the individual atoms inside the ion, but treat it as a unit. And be paying special attention to the fact that it may be in parentheses, which might mean you have more than one on one side of the equation. So just be paying attention to that. And lastly, balance H atoms and O atoms last. Do them last. If you have any other atoms in your equation, start with those, and then do the oxygen and hydrogen atoms at the end. The last step is then to count atoms to be sure that your equation is balanced. Eventually, you're going to get good enough at writing equations that you might be able to skip the steps where we write a word equation and then write a formula equation. But no matter how good you get at balancing equations, you should never skip this step. Because it's very easy to make a mistake without realizing it, and if you don't count them up at the end, you won't realize it until you've turned your work in. So always, always, always double check. Count them up on both sides of the equations like we did. There's 4 total hydrogen and there's 2 total oxygen, and make sure it matches up with the other side of the equation. Occasionally, you'll get to this step in the equation and you'll notice that you're totaled fine on both sides, but you will notice that it doesn't represent the least possible whole number ratio of reactants and products. Because sometimes in the process of balancing, we get some pretty large numbers. At this point, it's when you should check to see if there is, in fact, a greatest common factor. And if there is a greatest common factor, you divide by that greatest common factor to reduce your coefficients. And then once you've done that, double check that your atoms are still balanced. Okay? All right. There are lots of symbols used in equations, okay? The ones you are familiar with will be the molecular formulas and the formula units, and you are probably at this point in your science careers familiar with the idea of an arrow in a chemical equation. Okay? But there are many other symbols that will commonly show up in equations. And the following table that we're going to go through together summarizes some of the most common symbols and what they mean. All right. We'll start with the symbol you are most familiar with, which is just a straight arrow pointing from the left side of the equation with the reactants to the right side of the equation with the products. This arrow can be read to mean yields or produces or reacts to form. What it's meaning is that that arrow is where the reaction is taking place, and it's separating the reactant side from the product side of the equation. Sometimes you will notice that there is two arrows, one going each direction. Sometimes the arrows will only have half of a point on them, or sometimes it might be a double-headed arrow. All of those symbols mean the same thing. They mean that the reaction is reversible. Okay, which means that the reactants can form into the products, but the products can also react to form into the reactants. So the double-headed arrow just means that the reaction can go in both directions. Okay? Most reactions can go in both directions, but a lot of them are going to go more quickly in one direction, so you may not see that double-headed arrow all the time. If you see the lowercase letter s in parentheses after the formula for a substance, what that means is that that reactant or that product is in the solid state. If it's on a product and it wasn't on any of the reactants, it may be used to indicate that that new solid is a precipitate. In a similar fashion, that downward arrow that you see in the line beneath it is an alternative to writing S, but in this case, it is only ever used to indicate a precipitate, which means you would never see the downward arrow on the left side of the reaction. You would only ever see it on the right side with a product.
What did we say precipitates were?
Precipitates are solids that form from two liquids that are in solution, and the solids form and then they are not in solution. So like the blue substance we formed in our lab. Similar to the lowercase s in parentheses, a lowercase l in parentheses, sometimes, unfortunately, depending on the font, it's going to look like an uppercase I. But if it's in parentheses like that, you can assume it's a lowercase l, and it means that that reactant or that product is in the liquid state. That's pretty self-explanatory. The one underneath it is a little more complicated because the lowercase letters AQ stand for aqueous, which is a science way of saying that that product is dissolved in water. So the reactant or the product is, if it's aqueous, it's dissolved. So for example, if you saw NaCl with the parentheses AQ, you would know that we are talking about table salt, but that table salt is dissolved in water. Okay. And then finally, if you have parentheses around a lowercase g, that means that the reactant or the product is in the gaseous state. Okay, so letters in parentheses generally telling you about the state of the reactant or the product. You can use an upward pointing arrow as an alternative to a lowercase g in parentheses, but only to indicate that a product is a gas. So these up pointing and down pointing arrows are used on products so that you don't have to write out words in your equation to say, hey, this formed and it was a gas, or hey, this formed and it was a precipitate. You can indicate it with an arrow instead. So when we reacted our baking soda and vinegar with each other, we produced carbon dioxide gas, and it went off into the air. So when we wrote that equation, we could have written CO2 with an arrow next to it to indicate that it was produced as a gas. Now, under normal conditions, CO2 is almost always a gas because it takes really, 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 really intense cold temperatures to make it a solid. and it just goes from the solid state to the gaseous state. It often skips the liquid state. So most of the time, if you just write CO2, people will assume it's in the gas state, but we can give them more information. And then if you have an arrow in the middle of your equation, it still means that that is where the reaction is taking place and that it's yielding these products. But if it has that delta symbol over top of it or the word heat over top of it, they are telling you that in order to make this reaction happen, you have to heat the reactants. Most of the rest of the symbols we're going to look at involve some sort of indication about what condition the reactants need to be in order for the reaction to happen, and that information is almost always placed above the arrow. Okay. So, if there is a specific pressure that you need to put the reactants in order for the reaction to happen, they will put that pressure above the arrow. So in this case, it would take 2 atmospheres of pressure. So double normal atmospheric pressure would be required in order for this reaction to take place. Okay. If it was a different pressure, they would put a different number. And they might use a different unit for pressure than ATM. Okay. If you just see the word pressure written above the arrow, what they're indicating to you is that the reaction requires more than normal atmospheric pressure to happen, but there's not a specific number that it needs to take place at. So pressure would just mean you're going to need to pressurize this higher than atmosphere pressure in order for it to happen, but there's not a specific pressure you need to put it at. If there is a temperature listed in degrees over it, that is the temperature at which you need to carry out that reaction. So in this case, 0 degrees Celsius, which would be the freezing point of water, would be the temperature required to carry out this reaction. So it's going to need to be a little chilly. In science, you're almost always going to see temperatures in Celsius or Kelvin, but it would be possible to see them in Fahrenheit, just not as common. And then the last one, if you see a formula over the top of the arrow, that means that this reaction requires a catalyst. A catalyst is a substance that can alter the rate of a reaction, so it can make a reaction happen faster or make a reaction that might not otherwise happen. But what's important to note about a catalyst is that you don't need to include it on both sides of the reaction because a catalyst is not chemically changed during the process. So you can recover the catalyst unchanged from your reaction, so they put it over the arrow instead of writing it on both sides because it's not involved in the chemical reaction in terms of actually being consumed and changed into a new product.